Welcome, welcome, welcome. I'm Lisa Blackburn, and this is my YouTube channel where I talk about everything that I want to that is math and science. I really do have a YouTube channel, and so there's y'all will be able to see other videos too with math and science. If you like the way I teach, you can go watch the other ones too. Like if you don't like your math teacher, but you think you like the way I explain things, you can watch my math videos. Okay, so what we're doing today is we're talking about chemical measurements. And our standard that we're learning is this: to obtain, evaluate, and communicate information. And then we're just stopping right there because that's all that this is about, is how do we obtain, evaluate, and communicate information in chemistry. And what I said before the video started was that in chemistry, we can communicate with each other all over the world without speaking the same language. My oldest son was a chemistry major who just graduated. Now he's in a doctorate program, but he actually synthesized a compound that had never been synthesized before. He made something new in chemistry. And so to be able to do that, he had to look at research from all over the world. And so he would go online. We have this wonderful internet now. He would go online and he would watch videos from people in India and China and all over the world, and they would be speaking their language, but he could understand it because they would be writing on the board behind him. They would be writing chemistry. And he didn't need to know their language to be able to understand what they were doing and to learn from them. So we're very picky about how we do information in chemistry. And a lot of it is numbers. Okay, I'll put this down. Sorry about that. Okay. All right, so let's get started. What is the study of substances and the changes they undergo? What do you think that definition is? Chemistry. Chemistry. It's what it's all about. Okay, I'm going to change my color here to blue. I think it'll show up better. I'm not very good at writing with this. Well, I'm getting better though. The problem is I go too fast. You have to go slow, which is boring. All right, look at that. You can even read it. Okay, now, we have two kinds of measurements in chemistry. We have the kind that give results in a non-numeric way, and then we have a way that usually gives it in a definite form, usually numbers. Any guess what those would be? Anybody guess what those words are? If it's non-numeric, it's qualitative, because it has a quality, Q-U. So that would be like red. So color your red. We're coloring our notes. So color your red, and I'll color my red. I'm going to color it with a highlighter. Red. Let's see what it does. Ooh, look at that. That's pretty terrible. It's too thick. I shouldn't have used the highlighter. All right, let's go back to writing. All right. And so chemistry, that's our chemical right there. This is what you think of with chemistry. And qualitative would be like saying that something is red. It'd just be a description of it. The other one is quantitative. A quantity is how many. Quantitative. Yep, I'm writing messy again. It gives the result in a definite form, usually a number, like 3 centimeters. So draw a line to that. Now, we want to have, so first of all, types of measurements. Number 2 is we want to have good measurements in chemistry. So we have the ideas of accuracy and precision. Accuracy is how close something comes to the, what? The right? The actual thing, the right answer, the truth. Truth is important. The truth. And precision is how close a number comes to the same value. We repeat experiments in chemistry, and you want to get close to the same number each time. That means you're doing a good experiment. Or sometimes it's how finely stated it is. How finely stated. How finely stated it is. So, like I can say it's 3 centimeters, Or I can say it's 3.579 centimeters. The 3.579 centimeters is more finely stated. Now, it could be wrong, but it's very precise, isn't it? Okay, so this is sort of our idea. Right here, I have 3 arrows. So draw on you can color your bullseye if you want, color your arrows. But here I have 3 arrows close together, but they're wrong. Is that accuracy or precision or both or neither? 3 arrows right together. What was I? Accurate, precise, both or neither? Precise. I'm precise, but not accurate, right? I repeated it. I just repeated wrong 3 times. So this is precise. I'm going to put a P and draw it to that one. What about this one? Here, I've got them all over the place. So is it precise? No. One of them's accurate. That one's accurate, but they are not precise. So only that one is accurate. Both of those are neither. That's neither, and that one's neither. How about that one? The last one. It's accurate and precise, and this is what we want. We want it to be accurate and precise. That's what we're striving for, is accurate and precise. As precise as we can be with the equipment we can afford. Okay, the next thing is, oops, let me move that up. Is that okay? I'm not going too fast? Okay, the next thing is expressing measurements. Now, there's 2 different parts of this. The first one is we're going to use a thing called scientific notation. And it's a way to write really big and really small numbers. Now, why do we need this? Number one, it's easier. Instead of writing 500 or, more honestly, 23 zeros, and then a number, this is a way that it's a shorthand for writing numbers. And the other reason is our calculators. Okay, so on my calculator, my screen is a limited size. My calculator can do math on bigger and smaller numbers than the screen will allow. Does that make sense? So we can do a shorthand. Now, remember when you got to Algebra 1, your teacher said that we don't use X for times anymore. Instead, we use a dot or parentheses or a number sitting next to a letter means times, right? Everybody remember that. Once you get to high school, X is X. It's an unknown. It's a variable. We want to find out what it is. That is true in every area of high school except this one. We're actually going to use X for times. I know that feels like a step back, but it's just the way it's done in scientific notation. So this is the form. The proper way to write a number is a non-zero number, then a decimal point, then a couple of more non-zero numbers, then X meaning times, then 10, and then an exponent. So it's a number, point, any other non-zero numbers, times 10 to an exponent. Now, I teach this in math also. Did y'all already learn this in Algebra 1? I teach my Algebra 1 kids, I teach this. Did y'all learn it in Algebra 1 already, or is this new? New or old? Kind of old. Kind of old. You've seen it before in math? Is it new for some of y'all? I always learned my math in science class before I learned it in math class. Math was always catching up to science. I learned trig and physics. I always learned my math and science first. So maybe they've straightened that out. It was a long time ago I went to high school. All right, so here is the example. Here I have this number, and this is how you do it. You take the decimal, so the decimal would be right here. And we make it hop like a frog to its position, which is behind the first non-zero number, and we count how many frog hops it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this number is 1.23 times 10 to the 10th power. Now, normally I do this on the board, and I make the decimal point look like a little frog, because it's more fun. All right, did that make sense? Who needs me to do it one more time? One more time from the top. Okay, y'all seem to understand this. All right, well, let's do the next one. We're going to make this decimal point hop to its place, which is behind the 1, and we're going to count the frog hops. So you try it by yourself while I do it, and then you can look up and see if you got it right. So everybody try it yourself on your paper. Okay, did you get it? So it's 1, 2, 3, 4, 5, and then it's got to hop over the 1 to get in its place. So it's 6 hops. And because it is a small number, the exponent is negative. Really big numbers, the exponent is positive. Really small numbers, things that are less than 1, things that start with 0 point, those are going to have a negative exponent. Any questions about that? Nope. You are brilliant. You are doing awesome. Okay, let's go here. All right. So if it's a big number, it is a positive exponent. If it's a small number, it's a negative exponent. Okay, now, this is if you have your calculator. Now's the time to get it out so you can learn how to use it. On our calculator, there is a button for scientific notation. If you have the TI 84, 83, 82, TI 30, TI 35, trying to think of the ones that, I used to love the TI 25, they don't make it anymore. But anyway, what you're looking for is capital E, capital E. On the TI 80, 2s, 3s, and 4s, it is the second of the comma right there. So look on your calculator, and painted on it is capital E, and you would do second comma to get to it. Okay, if on some of them they have a button that says EE, some of them have a button that say EXP, some have SCI, and some have times 10. If you have your calculator, did you find the button? Everybody found your button? Okay, then let's put in some numbers. Okay, so on our display, it will display an E, which means times 10. When calculators were new, they couldn't do X's. They could only do things that do a grid of 8. I'm old enough to remember this. Y'all are not. So they don't use times. They do E, and it means times 10. So let's put it in. Let's try to put in this in our calculator with scientific notation. If you don't have your calculator, you can use your phone this time. Look at, if you've got an Apple, an iPhone, it's got the regular calculator. If you hold your phone this way, it turns scientific. If you do it that way, I'm off the screen. Vertical is regular, horizontal, scientific. Did you get an E or EXP button on your phone when you did that? Now, you put a lot of stuff in backwards on the phones. I don't want you to get in the habit of using your phone, but if that's all you got today, it's all you got. But we need to not use the phones, one, because you're not allowed to use it on the test. And for the phones, a lot of times you put in things backwards, and it will confuse you, and you'll get it wrong on the test. Okay, so let's put in this one. This number, we're going to move our decimal point 1, 2, 3, 4. So this is 3.6 times 10 to the 4th. Okay, so turn on your calculator and put in 3.6. Then hit the button that's EE or EXP or whatever. So I'm going to do second comma, and it put a little E on my display. That E means times 10. And so now I tell it 4, and it will look like this. It'll look like 3.6 E4. That's how your calculator will probably write it. Did you get it? Did you get your calculator looking like that? If you have a Casio, it's a pain, but you're looking for the times 10 button probably on Casio. Okay, so let's try this one now. 200, we would move it 2 places, and it would just be 2 times 10 to the second power. So put that one in. So you can just hit enter to make that one go out of the way. And now do 2e or EE and then 2. Now we want to try to multiply them. So we got in this number, and let's just say times, and let's put that one back in. 3.6 EE 4. Hit enter, and what'd you get?
7.
I got 7, 2, 0, 0, 0, and 5 O's.
5 zeros.
72 and 5 zeros. Look, I keep touching this. 72, 1, 2, 3, 4, 5. So try it again and see if you can get it. And then let's write this in scientific notation. So we're going to go 1, 2, 3, 4, 5, 6. It would be 7.2 times 10 to the 6. Now, the old TI-25s, you could do second EE equals, and it would put it in scientific notation for you. This one says error, syntax, quit, go to. We're going to quit. But the old TI-25s would go back and forth with it. Okay, how do we feel about that? All right? Okay, let's go on. Let's try this. Put these two numbers in your calculator and divide them. Put them in a scientific notation. Don't put them in straight. Practice putting it in scientific notation and then divide them. So this one is 7. This one is 3.3 times 10 to the negative 7th divided by 4 times 10 to the negative 3. Now then, so try putting that in your calculator. 3.3 times 10. Negative on your calculator, if it looks like this, is on the bottom. Minus is on the side. Negatives are usually at the beginning of numbers, but this is, and for exponents, minus is in the middle of your problem. And you can remember that because minus and middle both start with the M. But this will be negative, and sometimes your negative button is a plus minus. Okay, so this is negative 7, and then divided by 4 times 10 to the negative 3. And what'd you get? 8.25 times 10 to the negative 5. 8.25 times 10 to the negative 5. So notice I didn't write the shorthand my calculator did for my answer on the test. I write it in the proper form. Any questions about that? No? All good. Okay, next is something called significant figures or significant digits. Okay, so let me move that down. Okay, and this is how to round. Remember when you learned rounding in elementary school? Remember that? How to round a number? Well, we have a special way in science called sig figs and significant figures or significant digits, and I'll tell you in a second. And it's how far to round, okay? So if you don't know how to round, now y'all are like, I'm in high school, I know how to round. I tutor kids all the time who have learned this wrong. So we got to learn it. When you round something, 5 and up, round up, okay? That's not the part that people don't understand. Look only at the digit next to it to decide to round. There is a math curriculum that a lot of people use now that teaches this wrong. The way the math curriculum teaches it, if you have 17.253172, and you wanted to round to find out what that 2 should be, there is a math curriculum that says, okay, you start here, and 2 leaves the 7 alone. The 7 rounds the 1 up to a 2. The 2 leaves the 3 alone. The 3 leaves a 5 alone. The 5 rounds the 2 up to a 3. There is a math curriculum that teaches that you start here. You don't. You don't care about any of that. None of that matters. You only look at the number next to it to decide if it rounds up or down. This is too small. This is too insignificant of a value to have any impact on this huge tenth. That's tenth, that's hundredth, remember that? Okay, do you understand? Did anybody have that taught to them wrong? Anybody in here? Good, excellent. I run into it all the time. One time I was tutoring somebody in the library, and I was at the Dallas Library, and I was at the young adult fiction big table. And they had bookshelves of books there, and I was teaching this, and there was a young person on the other side, and finally they peeked around and said, I was taught that wrong. Looking through their books, they were listening to the math tutor. All right, now, why? Why do we need to know about how to round in class? We want to be honest scientists and not make our data look better than it is. If I put all of that big old number down for my data, it would look like I really measured something fancy, wouldn't it? It would look like I had a very expensive piece of equipment. It would make my data look like it was really good. And our calculator can give us a lot of decimal points as we do math on our data that would make it look better than it is, okay? So how you do this? So what my drawing here is I've got some and I forgot to bring it. Okay, well, I'll show it to you later. Let me go back and show you what I want to show you. Where's my thing? There it is. It's more fun with sound effects. Okay, so I have this really old-timey balance. It's a chemistry balance from, who knows, the 1920s or something. It's a box, and it's got scales on it that actually look like the scales of justice. You put your chemical on one side, you put little weights on the other side until they weigh the same thing, okay? So that was considered a good balance back before electricity was common in labs, I guess. All right, now what we have is something called an analytical balance, and we're going to use it for a lab. It's not in this room, it's in the chemistry room where the shower and the fume hood is, okay? In it, this thing costs thousands of dollars, so we're going to be careful when we use it. But it is so sensitive that wind will change your value, just currents in the air. If I go like this, it will change the value. So it's got little doors you close to make sure the wind doesn't blow on it, and it will tell you to 4 decimal places what something weighs. It was very expensive. So we don't want it. Our regular balances we use in here, where did I put those? I think I put them in the back. They are just these little pan balances, and they only go to 1/10 of a gram. So this is cheap. You can get these for $10 on eBay. This is thousands of dollars. We don't want to lie and make it look like we use the thousands of dollars one when we use the $10 one from eBay. Does that make sense while we do this? All right. So there are rules. When you do your math, rule 1 is you use all the digits. You don't do any rounding to the very end. At the very end, you round your answer and not till then. You use all the math you've got for as long as you've got it. Now, this is the rule for adding and subtracting. You round your answer to the same number of decimal places and the number with the least decimal places. Least. Okay, so least number of decimal places, that's what you round to. With multiplication and division, you round your answer so that your answer has the same number of significant figures as your number with the least number of significant figures. Now, what does that mean? These are the rules, okay? Whether or not you can figure out how many significant figures it has. So this is going to be on your test, so make sure you understand it. Here are the rules, and I give you the rules here and on several of your worksheets, so they're around. Number 1, all non-zero digits are significant. So in this number, 123.45, all of those are non-zero, so it has 5 significant figures. Does that make sense to you? We're finding out if we count the numbers or not, and if it's not a 0, you always count it. Rule 1. Rule 2, Zeros between two non-zero numbers are significant. So that zero counts because it's between two non-zero numbers. So 102 has 3 significant figures. Zeros at the beginning of a little bitty decimal number, like this, do not count. They're considered just placeholders. So this only has 1 significant figure. Zeros at the beginning don't count. Does that make sense? Okay, next one. Zeros at the end of a number after a decimal are significant. So if you have a decimal and then zeros at the end, they count. They were measured. So this one's got 1, 2, 3, 4, 5, 6. Okay, next one. Zeros at the end of the number with no decimal point are not significant. So 4,200 has 2. Don't worry. Once you practice it, it will be easy. Now, why do we have this little guy here? Because usually people do not say significant figures or significant digits. We're lazy and we're nerds, we're science nerds, so we do an abbreviation. And we either call them sig figs or sig digs. So this is my cool kid, and cool kids say sig figs. How many sig figs? So give him a little bubble. How many sig figs are there in this number? Because he's the cool kid. And I usually won't say significant figures. I'll say sig figs. And you need to know what I'm talking about. Okay, next, number 4. Changing between measurements. This is called factor label or dimensional analysis. And how you do it is you use a conversion factor. Conversion factors always equal 1. I teach this in math class too. Have you already learned this in math? I teach it in math, in Algebra 1. Okay, that's all right. You can learn it now. So these are things that equal 1. 1 meter is the same thing as 100 centimeters. 7 days is the same thing as 1 week. 12 inches is the same thing as 1 foot. Did y'all learn that rhyme when you were in elementary school? Stop, kaput, 12 inches in a foot. No? Yes, someone knows my stop kaput thing. Yay, that makes me so happy. All right, so mathematically, what we're going to do works is because they are the same thing, we're going to write them as a fraction. And anything divided by itself is 1, right? 3 divided by 3 is 1. So 7 days divided by 1 week is mathematically the same thing as 1. And anything that times 1 is itself, right? 36 times 1 is 36. So we can multiply things by a conversion factor, and we don't change its value, we only change its units. If that did not make sense to you, don't worry about it. There's always kids, though, who can't learn their math if they don't understand why. So that's for you. If you can learn it without understanding it and you don't understand, fine, don't worry about it. If you can't learn it without understanding it and you didn't understand it, talk to me later. I'll explain it to you again slower. Okay, because I know sometimes I talk too fast. I used to have students go, Miss Blackburn, where are you from? You talk too fast. We can't understand that fast. They're like, are you from up north? I'm like, no, I'm from Smyrna. That is not up north. Okay, how many seconds until break? Okay, so we have a fall break coming up. A winter break, wrong one, I'm saying the wrong one. And how many days is it till we get to go on break? Oh, well, we've got MLK Day on the 18th. So that would be 1, 2, 3, 4, 5, 6, 7. What?
7.
Let's do it to the let's do it to winter break. When's winter break?
15th, I think. Of February?
It is the 15th. So that's 1, 2, 3, 4, 5, 6 weeks minus a day. So 41 days. Does that sound right? We'll do 41 days till we get off for winter break. What?
You said it was far away.
It's far away. Okay, so this is how you use this. First of all, you write what you know. Now, we're going to do these problems for a long, long time and apply them in all different situations. And I'm going to say, what do we write first? And y'all are going to look at me confused. I'm going to go, we write what we? No. And y'all will all say no. Okay, so just so you know your cue. You're supposed to say no when I do that. So what we know, what we are given is 41 days. and you write it first, write what you know. Then you're gonna draw, and I meant to draw a train on here. This is called train tracks, but it doesn't really look like train tracks, but that's what we call it. It represents fractions. So things written on top of the line are numerators, things on the bottom are denominators, and we're gonna write the unit of what we know in the denominator. Okay, are we okay so far? Write what you know, write the unit of what you know in the denominator. Then we think, do we know how to change it into seconds? Do you know how many seconds are in a day? Last semester I did, but I had one girl, but we're going to pretend like you don't. Okay, I don't know that, but I do know how many hours are in a day. And so I can make that relationship, that thing that equals 1, there's 24 hours in one day. Now I continue adding to my train tracks by writing my days are going to cancel out, because if you have the same thing in the numerator and denominator, you get to mark them out, right? Okay, so now I want the hours to mark out, so I'm going to put them in the denominator, and I still don't know how many seconds are in an hour, but I do know how many minutes are in an hour. And it's 60 minutes is 1 hour. That's the relationship, right? Those are 1. Now I'm getting somewhere. Hours mark out. I'm left with minutes. I want to get rid of minutes, so I write it in the denominator. And I can now change it to seconds, because there's 60 seconds in 1 minute. Any number on top I multiply. Any number on bottom I divide. Ones you can skip. So on your calculators, do 41 times 24 times 60 times 60. If any of these were not ones, then we would have said divided by that number, but they're all ones. So what did we get? What's the answer? Say it loud. 3 what?
3542400.
Is that it? 3542400?
Yeah.
That's a lot, isn't it? And minutes cancel out, and we're left with the unit of second, the unit we want. Now, this is dimensional analysis. Dimensional analysis means you look and see if when you do the math to the units, do you end up with the right units? And that will save you in physics so much. If you will always check and make sure that you get the units of what you're supposed to. Say if you're getting speed at something like meters per second and not degrees Fahrenheit, then you know you might have done your math right. Okay, so that is, okay, and then how many centimeters in 4 feet? What are we going to write? What we know. So 4 feet. Okay, what goes on the bottom? Feet, because we want to mark it out. What's the relationship between centimeters and feet? Don't know it, but I do know feet and inches. That's in inches. Stop could put 12 inches in a foot, and that's an inch. It's really hard to tell. And I do know the relationship between inches and centimeters. There's 2.54 centimeters in an inch. Multiply anything on top, divide anything on bottom. You can do it later. I just wanted to show you another one. Okay, next. International measurements. In science class, we use measurements that can be understood all over the world. It's easier. But what we use is Le Système International de Units. Perfect French, nailed it. Or SI. We also use the metric system, which has got a lot of overlap with SI. And we use metric also. So, what are the base units in the metric system? What's the unit of length? Is it inches and feet? No, that's English. It's meter. Meter. Do I need to write out meter, or can I just put an M? I'll write out meter for you. So you can draw a little arrow down to your meter stick. Okay, so a meter is this big. 3 inches longer than a yard. That's a meter. Okay, how about mass? What do we measure that in? Sounds like a cracker. Gram. Gram. And see, we have the kilogram there. What do we measure time in? Well, same as English. We're going to say second. That's the base unit. Current, this is not talking about like row, row, row your boat. This is electrical current. Anybody know what it is?
It hurts.
Nope.
That's not.
It's the ampere, which is amp for short. You ever buy an amp for your car stereo? That's why. Temperature in SI is Kelvin, which we don't use much, but we use Celsius instead, which is metric. Fahrenheit is English. For volume, we use liters. Or cubic meter. And you need to memorize that 1 cubic centimeter is the same thing as a milliliter. Memorize that. It will be on a test, so make sure you know that fact. Energy, we use joules. And that's not like diamonds and rubies. It's spelled different. Joules. I know I'm writing fast and it makes it really messy. Pressure, it has a bunch of them. One of them is called a Pascal. One of them is millimeters of mercury, which is written like that. Little m, big H, little g. And then another one is atmospheres, which is abbreviated ATM. And you'll learn more of that when we do the gas laws. Now, an easier way to convert if it's metric, remember I told you metric is easier, is this. King Henry's daughter bakes delicious chocolate muffins. See the muffins? Don't they look delicious? Okay? And this is how it works. The K stands for kilo. The H stands for hecto. Sounds like people's names. The D stands for deca, like the club here, but with the C. B stands for basic. Little d stands for deci. And you can remember it's deci because all the things that end in E go together. Deci, centi is C, and milli. Why is that writing it? There it goes. I confused it. And milli is little m. So you can frog hop to change things without doing the dimensional analysis thing. So if we want to change 4,800 kilometers to millimeters, we look and see where we start and how many frog jumps it is to where we want to go. We're at kilo. Oh, we're almost out of time. This will be our last thing. And we want to go to milli. It's 1, 2, 3, 4, 5, 6 frog jumps in this direction. So we take our decimal point and we go 6 frog jumps in that direction. 1, 2, 3, 4, 5, 6. You add a 0 for every jump, and that's how many kilometers is millimeters. It's 4800,000,000 millimeters. Now, I want you to stop there, and we will stop this and come back and add more later.